Hello, my name is Mariusz Sabat and today I'll be talking about protecting data using secret management with trusted service identity. This work has been done in IBM Research by Brandon and myself, and our executive leaders are Gosia Steinder and Ala Youssef. We also have a very close relationship with Daniel Pittner from IBM Cloud and Cognitive Software. So, what is the problem? Today, if the microservice needs to retrieve or exchange data with some other external or internal service, it must authenticate itself. This authentication requires secrets, password, API keys, certificates, and etc. that are typically stored as Kubernetes secrets. Even though Kubernetes secrets are designed to be stored securely by the orchestration, they can be simply read by anyone who has access to the namespace, including cloud operators. Those knowing the secret can also access the sensitive data that needs to be protected. The problem is that operators or admins might not be certified to access this data, that they might lack security clearance or legal requirements like specific citizenship. On the top of it, there is an increasing need for accurate audit trail to track who, meaning what process, access what and when. Let's take a quick look at the hypothetical scenario in today's practice. An application composed of several microservices is deployed in Kubernetes cluster. These services, made of containers, need to access cloud and database with some sensitive data. The cluster operator generates certificates or keys and stores them in Kubernetes cluster as Kubernetes secrets. Problem is that cluster operator, administrator, or anyone with access to this namespace can also read the secret, and this means they can also read the sensitive data stored in the database. Another problem is that secrets are static, meaning typically the same secret for accessing database would be given to all instances of the application, and that makes the audit much harder in case of the lost or compromised secret. The application secrets are managed by the cluster operator instead of the secret owner. There is a lack of separation of duties. Finally, the secrets have no limited lifetime. So one solution is to introduce Vault, an industry standard tool for securely managing secrets. Vault provides a unified interface to any secrets while having a tight access control and capabilities to record detailed audit log of all the activities. We could move all the secrets to Vault, but we still need to authenticate the application somehow to be able to read from Vault. So we have to store in cluster a secret that allows the application to access Vault secrets. While this solution is more secure, anyone with access to the secret can get keys from Vault and still read the sensitive data from the database. In addition, humans create and inject the secrets to Vault and to Kubernetes. So secret management techniques in use today make secrets accessible to the cluster administrators. So we have compiled a comprehensive list of common issues with Kubernetes secrets and the threats originating from these issues. For example, application secrets and keys are static. The threat is that blast radius is wide with no accountability of the lost secrets. Application secrets are managed by the cluster operator instead of the secret owner. Cluster operator has access to secrets, thus can use them to read sensitive information and etc. Lack of process for secure delivery of secrets to correct applications. Cluster operator can read Vault authentication information, then read the secrets from Vault, then access the sensitive data. The first three issues are mitigated by using Vault, but what about the rest? The IBM research team has been working closely with Cognitive Software Group to address these problems. The solution is called TSI, Trusted Service Identity. As a result, Kubernetes admins cannot view the secrets because there are no secrets stored in the cluster. They are stored in the secure vault, which is significantly reducing the attack vector. TSI retains full audit trail, so we have a detailed record of who, meaning what process, got what and when. Permissions are enforced based on workload identity. Policies and permissions can be dynamically modified, keys revoked without changing anything in the deployed applications. Access to data might be dynamically terminated, and secrets might expire as needed or be simply rotated. Our solution allows for very fine-grained access control. So how is it done? First, container gets assigned a short-lived measured identity in form of a JWT token, a digital biometric, signed with the root of trust. Then we have policies that define what identities can get access to what secrets. The secret store, for example Vault, validates the token signed by intermediate authorities, and lastly, secrets are released to the workload application based on their identities and policies. Here's the architecture overview. In the pictured example, we want to protect access to the sensitive data in IBM Clouded. We also have a Kubernetes cluster extended with TSI, where each node gets intermediate CA signed by root CA during the secure bootstrapping of the cluster. Each node also has a JWT signing service that contains signing authority. This can be a software or hardware like TPM. Root CA is securely stored in Vault, and Vault is extended with our authentication plugin. So before we begin, Chief Information Security Officer or some other secure process deploys in Vault secret key for accessing the cloud and database, then creates policies that define what are the characteristics of the ANA application that can get access to these secrets. Now we can deploy an application in this cluster. This application wants to access the cloud and data. The deployment must include the annotation that describes what secrets are needed by this application. Our modified admission controller starts the sidecar for this application pod. This sidecar collects the measurements about the application and sends them securely to the signing service as claims. Signing service signs the claims using the intermediate CA and returns JWT token back to the sidecar. Sidecar requests the annotated secrets from Vault by passing JWT token along with the request. Our authentication plugin in Vault intercepts the request call, validates the signature and the expiration date on the token, and if everything is okay, it uses the provided claims against the policies to retrieve the secret. If the provided measurements match the policy, the secret is released to the sidecar. Sidecar mounts the secret to the running container the same way as the regular Kubernetes secrets are done. To reiterate, the secret has been delivered to the container runtime memory without being stored anywhere in Kubernetes environment. But from the point of view of the application, there were no additional changes needed. Here's the sample of the measured identity in form of a JWT token. It is composed of three parts: the header, payload containing the actual claims, and signature for validation. These claims included here represent the measured identity of the application. Few of them are static, assigned during the secure bootstrapping of the cluster, like cluster region, for example Germany, data center, cluster name, and individual machine ID, which is the worker node. There are also some runtime measurements like unique pod ID and the list of images making up the pod, including the image signature, so the image can be validated and guarantee that the application is running the code that you really want to be running. and it was never tampered with. There is also an expiration timestamp, typically set to 60 seconds, so these tokens are quite ephemeral and short-lived, protecting the security from leaking. Let's take a quick look at the policies. The access to the secrets is controlled by policies. Policies, along with the secret keys, are stored in Vault securely. So there is a clear separation of the secret management from the runtime environment. Our TSI Vault authentication plugin supports various policies. To build a policy, we can use a number of attributes that make up the measured identity. For example, one policy could be a region, cluster name, namespace, and image. Another one, less granular but much more common, region and image name. Let's use this one as our example. It's called TSI Policy RI, region image, and provides the read access to the secrets. When we deploy the policy, we register the Vault path that can be used to store the secrets. Simply put, the policy allows the read access as long as the container is running from a specific region and it was instantiated from the specific image. Now we can create a secret. It will be in a path secret, the name of the policy, specific region, and a specific image. By the way, image is the base64 encoded SHA. Then, in order to pass the secret to the application deployment has to include the following annotation: the actual secret name, the constraints, in this case region and image, and the local path where the secret should be mounted inside the application container. Now, let me show you a quick demo with TSI deployment. Okay, I will start by initializing the namespace and create this quick alias KK to make my typing faster. I will use the namespace trusted identity. Okay, let's test it. There's nothing here because I just created. Good. So now I can go to example directory and instantiate Vault. I would create the instance of Vault at the same namespace, just to make things easier for the demo. Vault instance is running. Since I'm running in IKS, IBM Cloud, I need to define ingress. I will use the ingress template. So I copy this template and change the value to my cluster name. My cluster, I'm running this in Europe, Germany. My cluster name is TI Test 1. So I'll save and initialize. Now I can create the ingress. It's up and running. I'll capture the Vault instance address, external address, and get the root token from the log file. Now I will test the access using login with the root token. It's operational, good. Now we can run the Vault setup. The Vault setup would define the root CA and would load the policies, the sample policies that we're going to be using in this demo. Now the policies are loaded to Vault and they are securely stored there. I'll copy the Vault address and start another panel, the console, the green one, which represents the secure bootstrapping, which we're going to do manually today. So I'm using this script to obtain the cluster information from IKS and define the values which I'm going to use to start the Helm deployment. The first deployment is the setup, and of course I'll pass these values manually. It would be done typically through secure bootstrapping. So the setup is operational. Now we can do the actual deployment. I need to have a Vault address, region, and cluster. Again, in production, this would be done by automated process. Now I pass this manually. Once this is completed, I validate all the components are operational and running. So now I can register this cluster with this root CA. What this process does, it copies the intermediate CAs to individual worker nodes. Once the setup is completed, I don't need the setup components anymore, so I would remove them by removing the Helm deployment. The first deployment is deleted. Let me verify. At this point, I should have only the JSS servers running on every worker node, the webhook, and of course our Vault service. Now I can deploy an application. This blue panel represents the application deployer. I will create namespace, test, and of course set up an alias. Let me show you the deployment file. So there is a request to inject secrets by annotation, and also request to obtain two secrets, secret 1 and secret 2. The first one uses region and images constraint, and the other one just a region. To populate the secrets in Vault, I can use this handy tool, Secret Maker. I have to just point at the deployment file and the namespace that would be used, and this builds the script that injects the secrets to Vault. So I can redirect the output to a script, and let's inspect it. I can define the value for my secret. Let's do it 1 for all of them. Of course, I can do individual values for individual secrets, but for the demo, it's 1 is okay. Down below, I have two entries. One injects the secret 1 using region and the image, the proper image name, and the second one is only using the region. Now I can run the script and inject the secrets to Vault. Back to the application deployer console, I will create the application. TSI would create a sidecar, that's why we have two containers running. I can exec to this container. Of course, we would disallow in executing two containers in production, but I want to show you the secrets. If we go to the requested location, my secrets, that's the one that was annotated, I have two secrets, my secret 1 and secret 2. Let's inspect their values. Here you go. These are the values that we defined in the injection script. So what happened is the secrets were delivered to an application without being stored anywhere in Kubernetes. They were securely stored in Vault only. This concludes the demo. Here is the sample list of use cases that we can address using this trusted identity model. Permissions to secrets can be enforced based on the workload identity or geographical location. For example, some applications must adhere to GDPR standards like this one. Data about Europeans can be only accessed within European geographical boundaries by an application that was well tested, validated, approved, and continuously monitored for compliance. Selected image versions must be executed only in specific data centers, accounts, and clusters, or provide a short-lived access to data using quick expiration dates. Automate the frequent key rotation without modifying an application. Common deployment code across multi-clusters and multi-geographical distributions with the location-based data restrictions. Different data feeds for different environments. So for example, development and staging gets different data than production. Fine control the dynamic release of secrets and configurations at the runtime or specific time. So let's go back to our list of issues with Kubernetes secrets. We know that Vault solves these three. Now let's look at the other ones. Using TSI with Vault removes the several other threats, like for example, cluster operator has an access to Vault and can read secrets there and use them to access sensitive data. Lack of location-based restrictions enforcement, preventing the geofencing. Malicious user can access data from unauthorized location, or unauthorized application can get access to sensitive data. Using Vault with TSI and TPM removes another threat, when the cloud provider is able to violate the software-based chain of trust. Lastly, when we add the trusted execution environment, we can protect host kernel from reading the container memory. These are just few sample issues. The complete list is available at the provided link. Let's reiterate the business values of TSI. Increase security by eliminating Kubernetes admins' access to secrets and data. There are no secrets stored in a cluster, which is significantly reducing the attack vector. Improved operational overhead, and it provides detailed audit trail. Provides the best practice patterns for secret management and distribution. Addresses several security compliance requirements for FedRAMP and HITRUST. In compliance aspects, provides consistent and standardized way for enabling compliance controls. It's reusable and easily deployable tooling. Automated, eliminating human error, thus agile and scalable. Significantly reduces operator work due to compliance modifications. Streamlines DevOps process for managing secrets. Provides tamper-proof hardware-based root of trust, and provides location-based restriction enforcement. We have open sourced our code on GitHub, and the images are also publicly available on Docker Hub. We wrote several blogs in IBM Developer and Research blog, Medium, etc. There are also a few relevant videos in YouTube, and we filed a patent last summer. And I just want to give a quick shout out to my friend Brendan, who's the co-author on this project, and he presents on another session here titled Running Trusted Containers on High Assurance OpenShift Platform. And at the end, thank you all for giving me the opportunity to present to you here on this conference. Thank you.